Hey guys, me again on video. I really, really wish I was at school, but when vomit is coming out of your kid and it's going everywhere, then you probably need to stay home. So, unfortunately, I'm home. I'm hoping to be back next week. Hopefully, things are all okay. Um, so we're just gonna make it as best as we can. Okay, so we're gonna go with some more video notes. I'm gonna try and go through as much of this as I can, as quick as I can, so that I give you as much information as I can to let you get through and get into what you need to. We're gonna talk first about what's called state functions. Okay, um, and a state function is really we can think about distance versus displacement. Okay, and in this example, where everybody's going to start here at the bottom of the mountain, we're going to end up at the top of the mountain. So we're starting at 0 feet, ending at 10,000 feet. You got path A and path B. Path A kind of zigzags and goes up the side of the mountain a little bit, and travels a greater distance than you would if you were traveling on path B, right? Path B goes straight up the mountain, no zigzags, no funny business. We're getting from the bottom to the top as quick as we can. Now, that is a shorter total distance traveled, okay? But it's still the same displacement, right? From whether you're on path A or path B, you are displaced from 0 to 10,000 feet. You're displaced by 10,000 feet now. Okay? Displacement is a state function. It does not depend on the path, on how you get up there. It just depends on your starting point and your ending point. Okay? Energy, I should say change in energy, delta E, is a state function. Okay, it doesn't depend on how you get from initial to final. It just those are the only two numbers you're worried about, initial and final. Okay, so let's move on here. We're going to talk about this here briefly. For some reason, the textbook notes don't mention anything about endothermic and exothermic. Okay. But in thermochemistry, endothermic and exothermic terms are very important to know. So here we've got a reaction, right? We've got carbon, oxygen, carbon dioxide. We're going to talk about the combination of carbon and oxygen to form CO2. Okay? So what this first bullet point is saying is that the total amount of energy in 1 mole of carbon and 1 mole of oxygen is greater than the energy in 1 mole of carbon dioxide. Okay, so in this case, this side of the reaction has more energy than this side of the reaction. Okay, so as we go, let's say this number, I'm just going to throw out numbers. Let's say this number is 500 and this number is 250. 250 joules of energy have to be released, right? So 250 get carried over, 250 are going to get released. So there is a release of energy into the surroundings. So the reaction, delta E, the change in energy of the reaction, is going to be negative. It's losing energy, right? It starts at 500, goes down to 250. Delta E of the surroundings, which is where this 250 is going, is positive. Okay, it's not written in there, but it's kind of understood that this is positive because it's gaining 250 joules up here. Okay, this would be considered an exothermic reaction. Okay, you need to write this down and you need to know exothermic. It's a term that I'm going to use often. If the book doesn't use it, I'm going to. Okay, so when delta E is negative, that is an exothermic reaction. It is giving thermal energy out of the reaction. It's exiting the reaction. It's going to the surroundings. Okay, now let's flip it. Let's go from carbon dioxide into carbon and oxygen. So now we know that this side now, let's say this side has the 500 and this side has the 250. Okay, now there's an absorption as this reaction goes on. There's an absorption of 250 joules from the surroundings. Okay, so the reaction itself is now positive. It's gaining energy for this thing to happen, and that energy comes from the surroundings, and so my delta E of the surroundings is now negative because this 250 joules is leaving the surroundings and going into the reaction. Oops. Okay, so this is what we call an endothermic reaction, where delta E is positive. Okay, endothermic energy is going into the reaction. Exothermic energy is being released from this reaction. Okay, you're going to kind of see some of these images of energy diagrams. Okay, and in this case, my reactants are on top. My energy level, see, internal energy increases as you go up. It's going down. So this is an exothermic example. That's supposed to say exo. Okay, as we release energy to the surroundings as we go from reactants to products. Now, if I go here, and these are my reactants, so this is the second equation right here, right? New slide, but same content. Now, in order for this reaction to go, I have to absorb energy, and this would be an endothermic diagram. Okay? Okay. Just real quick, I'm not going to spend too much time on these slides, but again, if we're talking system to surroundings, delta E is negative here. So this whole situation here describes an exothermic process, and you can pause this and write these down if you want to, but this is an exothermic process because energy is going from the system into the surroundings. Now if I reverse this arrow and delta E of the surroundings is negative, delta E of the system is now positive, this is your endothermic reaction. Again, you can pause this and write this down if you need to. I'm going to keep going. Okay? And I'm going to go here. We're going to stop here for just a quick sec. This equation right here is going to be helpful in solving one of your homework questions. Okay? The delta E is equal to the heat plus the work that's done on a system. And I think the question might be about pistons going up and down. And it gives you a couple of values for the heat energy that's involved and the amount of work energy that's involved. Okay? Now it says here that Q and W are not state functions. Okay? Their value depends on the process. So obviously, if you are walking zigzag up a mountain, you're probably putting in more total work than you would if you just went from point A to point B straight up the mountain. Now, that might be a tougher process, in the short term, but if you're thinking going zigging and zagging and zigging and zagging all the way up the mountain, that's probably more work. Okay, so work and heat are not state functions, but delta E is. Okay, and so here we got, these are positives and negatives, and you can kind of go through this chart here on your own. And if you guys have any questions, please write them down in your notes or try and remember them so that you can ask me and we can get some things straightened up and cleared away. Okay, let's keep moving, trying to get as much covered here as I can in the time of our video. I got about 5 minutes or so. Okay, so just a couple of things. So we're going to kind of switch away from the delta E and the heat plus the work for now. We're going to kind of go into the MC delta T, or the MCAT equation, Q equals MC delta T. Maybe that rings a bell from your previous chemistry classes. But heat is the exchange of thermal energy between two things, right? And we're talking about systems and surroundings here, right? So a chemical reaction and the surroundings that are involved. So there's a heat exchange, an exchange of energy when we have difference in temperature. If object A and object B are contacting each other, but they're at different temperatures, then we have a heat exchange, okay? That heat exchange results in what we call thermal equilibrium, where we have an equal temperature. Thermal energy on two objects is the same. Okay, so let's say object A is really hot, object B is really cold. Put them together, there's going to be a transfer of energy from one to the next. And that transfer of energy is going to happen, and it's going to continue until those things are at the same temperature. When those things reach the same temperature, that's called thermal equilibrium. Okay? And that thermal equilibrium is an important concept as we move forward here into heat capacity and Q equals MC delta T. Okay? Not going to spend a whole lot of time here. So we have something called heat capacity, which is different than specific heat capacity, but I'm going to kind of use them interchangeably. All right. So this is basically just saying that the amount of heat that gets absorbed is proportional to the increase in temperature. The greater the increase in temperature, the greater the amount of heat. That goes, that's kind of common sense. Okay. So some things that affect heat capacity. Every substance has a different value for heat capacity. So one of the things that affects it is the type of material. Water absorbs and releases heat at a different rate than does metal, right? And that makes sense. That's why metal makes up your cooking pans and pots. It translates heat really quickly. Rubber does not. It takes a lot of time for water to boil. Okay, so it doesn't absorb heat very quickly, but you put a pot, an empty pot on a stove, it's going to heat up really quick. Same, the other thing that affects it is the amount. So it takes more energy to heat up more water. That just makes sense. Okay, you got a greater amount of water, it's going to take a greater amount of energy to heat it up. I take a picture of this little chart right here. It has lots of different values for the specific heat capacity of different substances, and there's a couple of questions in your homework that deal with different substances and their heat capacities. Okay, so the specific heat capacity of water is 4.18 joules per gram degrees Celsius. And the way I write that is joules per grams degrees Celsius. Grams and degrees Celsius are multiplied together on the bottom. Okay, and that's the unit for specific heat capacity. All right. This is the equation I wanted to get to before we were done today. This is your Q equals MC delta T equation, and this C sub S is the specific heat capacity. I oftentimes leave off the S, but if you see C sub S, that's talking about the specific heat capacity of whatever substance. Okay, and we talked about the mass and the specific heat of the material being important here. Okay, but what this equation allows us to do is calculate the quantity of heat absorbed or released if you know the mass, the specific heat, and the temperature change. Okay, so delta T, remember, is T final minus T initial. Delta is always final minus initial. We talked about that with delta E, right? Final minus initial. So the question can ask you for any of one of 5 unknown variables. It can ask you for Q, in which case it's going to give you everything over here. It could ask you for mass. It could ask you for the specific heat capacity, or it could ask you for TF or TI. Okay? And then you just have to use your algebra skills to to solve for what you need. I'm at 10 seconds left. I'm sorry I couldn't get through more. Get as far as you can on your mastering chem today. We'll take care of things when we get back, all right? So don't worry about that. See you guys. Have a good one.